Hello everybody. Today we are on the 8th week and second session. We are solving some problems related with midterm and final exams, and today we are completing all the issues related with synchronous machines. So let's start. But before starting solutions, I wanna mention that here are also Turkish versions of related problems you can find here on my webpage. Okay, let's start. That is the summer school midterm exam question. Having 60 points. Today we are dealing with a bit complex problems. First, read the problem and understand the topic and try to solve the questions. First, that was an online exam, so only results are required. The format is given here. The angles and signs of angles are important. It is written. Let's read the question. A three-phase, two-pole round rotor star-connected synchronous generator with a synchronous reactance of 10 ohms operates in parallel with an infinite bus 50 Hz network having 400 volts face-to-face voltage. Okay, what does all those mean? Here is a network having line-to-line voltages of 400 volts, and somehow the generator is connected to that grid, infinite bus system, that is infinite bus system. Infinite bus means, infinite power means the voltage on the grid cannot be changed and it is constant. So V1 is, or V1 line, is equal to 400 volts and it is constant because that is grid, that is the property of the grid, and frequency possibly 50 Hz, it is constant. Infinite bus means, or grid means, the voltage and frequency cannot be changed by a single generator or load. We have a generator connected to infinite bus, that's it. Here we have 400 volts between phases. And our generator has two poles. Yes, two pole, one pair of pole. And it is round rotor. It is star or delta, star connected, three phase. Okay. Possibly here's a excitation circuit, but it hasn't been mentioned yet. Here possibly a prime mover. Prime mover supplies some mechanical input power in terms of torque and speed, and then possibly that power will be delivered to grid, converted and delivered to grid. Let's continue reading. Yes, it was 50 Hz and 400 volts face-to-face voltage. Mechanical losses and armature resistances are neglected. It means there is no frictional and windage losses. We call total mechanical losses. It is neglected. And array is neglected. Since array is neglected, copper losses in armature is assumed as 0. That was the definitions. One more. Machine is magnetically linear without saturation. Okay, there's no saturation, linear. That is an extra information. generally we don't use that. Just assume it is constant, you know. That was the definition. And as a first case, there are two different cases. In the first case, the generator delivers such an complex apparent power to the grid. So apparent power is equal to real power plus J reactive power. J is the complex variable, so you know the complex power. Here in this case, power is 1000 watts and reactive power is 0. There is no reactive power here in this case. So apparent power in magnitude, it is 1000 volt amps. That is the first case. Okay, let's define all those information into MATCAD. 400 volts on-grid operation, 50 Hertz, complex variable, let me say I is defined. Delivered power, let me say P1 is 1000 watts. There is no reactive power given, so apparent power can be written like this. And then as a result you observe only some active component. The original question is parametric. It changes with respect to student number. That is the final digit of student number. There is a parameter defined K, and it changes with respect to student number last digit. So here are also 4 different variants. I only deal with the first variant, and possibly there are 40 different results of this question. I recommend you to examine other variants. For example, in this variant it is star connected. Possibly some of the others connected delta, or here are some reactive powers possibly. Perhaps voltages and impedances are different. Let's continue on English version. I have only chosen the first variant with a student number of last digit of 0. Okay. And the question, write the load angle in degrees together with its sign. Its sign must be positive since it is operated as generator. Let's find it and interpret whether it is positive or negative. Our aim is to finding out delta, load angle. How can we solve this question? There are possibly a few methods, but we should choose or try one. Let me write the formulas can be used. Here is Kirchhoff's voltage law for equivalent circuit, EF. That is 0. That is 10 ohms. Excess terminal voltage, EF. Generator operation current is outgoing, so let's write Kirchhoff's voltage law around the loop. J, I1, excess, all those are in phasors. Do not forget J. That's the one of the equation can be used to find out delta, because here is EF delta, V10, which is reference, J, I1 phase angle, then here is excess. It is given. I'm not sure if it is given. This is given. In fact, line to line voltage is given. Consider what it would be. One of the approach will be this. The other approach will be this. Induced power can be written as 3 times single phase amplitude voltage. EMF over excess times sine delta, and we want to find out delta. We know how much power is delivered or induced possibly. In the question, here's a synchronous generator. We apply some mechanical input power, and then that mechanical power will be converted into electric power inside the generator, and after some losses possibly, here is the electrical output. Here would be some mechanical losses which is omitted here. There is no mechanical losses and armature resistance. So here would be copper loss in armature, but it is also neglected. That means mechanical input power is equal to converted power or induced power inside the armature, and it is equal to delivered power to the infinite bus. Now, so we can use this guy. We have already given. Here is the power. So we can substitute it here. We know this. We can calculate this. It is given. I don't know this. It gets more complicated. Let's read again. Let's choose the first approach. Start from here. Let's write the Kirchhoff's voltage law around the loop. Here's the equation. There are some unknowns. Since machine is connected star, we can write single phase voltage by dividing line to line voltage by square root of 3. So we can easily calculate single phase voltage here, as you see. And then we don't know the current. Houston, we need current, but we don't know current. But again, it can easily be calculated. It can easily be calculated because the amplitude is given here. Apparent power is given here. It is equal to square root 3 times line to line voltage and line current. It is given as 400 volts. It is given as 1000, as we have considered here in the question. The amplitude is 1000. So it can easily be calculated. Line current. So let's calculate it. Line current. I copy some parameters from here on my next page for easiness. That is the case. Apparent power was this over square root 3 and line to line voltage. So that is the line current. Since it is star connected, it is equal to single phase or winding current. Okay, we have checked it out. I1 is calculated, ladies and gentlemen. I1 is okay. And now we can substitute all those informations here, but remember, all those parameters in that complex equation are phasors. So current has some phase angle. What is the phase angle? What's the phase angle? Power angle or phase displacement is equal to arctangent reactive power over active power. Here it is 0 and power is 1000 watts. So phase difference is 0. Machine is operated as pure ohmic generator. So we know the phase displacement, and you can there's no imaginary part. I mean, I1 phasor is equal to something like this. There is no imaginary part due to no phase displacement. So it is easy to write down here. Okay, let's summarize what we have done. We need phase displacement. Phase displacement is the argument of apparent power, conjugate of apparent power effect. That means conjugate, or otherwise you should interpret the sign of the phase angle. I mean, phi is the argument of complex conjugate of complex apparent power, because if reactive power is positive, phase displacement is negative. There is something reversed due to complex conjugate operation. If reactive power is negative, in such a case phase angle is positive. That as a result of complex conjugate operation here in this. Here it is a bar on the apparent power. That means complex conjugate. Phase displacement is 0 degrees and meaning full resistive loading. Okay, we have already know this because there is no reactive power here. And V1, here it is. I1, here it is. XS, we know XS. So EF can easily be calculated, has such a complex value. So amplitude of EF is given in, let me write it down here. That is the amplitude of the complex number, and let me calculate the argument of the EF. Let me say delta 1. That is the angle of EF. Remember, here is delta. So arctangent imaginary over real part of these EF complex number result in delta. Here is delta, which is argument of EF complex parameter, and it is 3.5 degrees. Okay, let me check it out whether I am in the right way or not. Yes, I am on the right way. 3, 5, 7, 6. That is the lot angle for the first case. Okay, let's read it. Read the question again. In the first case, write the lot angle. It was very easy to get 15 points. Okay, let's continue. As a second case, in the second case, after the above operation, let me change color. After the above operation, operating conditions, the driving torque of the generator is doubled. In the second case, torque input is doubled. So, possibly, since speed is constant, mechanical input power is doubled. There's no mechanical losses and copper losses, so output power is possibly doubled. Okay, let's continue reading. The driving torque of the generator is doubled without changing the excitation current. Houston, there is an information. There is no change in IF. It is constant during the cases. From case 1 to case 2, IF keeps its value constant. Okay, what does it mean? If IF constant, flux will be constant, and as a result, induced EMF in armature will be kept constant or stay constant. There's no change. That is a clue. Excitation current without changing. So it is constant. What does it mean? Magnitude of the EF is constant. Houston, what is the magnitude of EMF? Houston, here it is. Second case, let me write it down here. Second case. Second case, IF is constant. So magnitude of EF stay constant. Stays constant. Okay. So in the second case, EF is this. But we don't know the delta yet, because there is, you know, what we are doing to control active power change. If you increase input power, you will increase delivered active power. That is the active power adjustment method. To increase output power, you should apply much more torque. So in the question, input torque is doubled, so output power has changed. But during that change, I assure you that delta will change. Remember phasor diagrams we have already discussed in active and reactive power adjustment. Delta will change. In the second question, write down the new value of lot angle now. New value of the generator in degrees, and its sign must be correct. It is positive, it is generator. We have already calculated one here. let's talk on sign. It's positive since it is operating as a generator. Okay. Now new value is asked. New value asked. What is the new output power? New output power, let me say P2 is double of P1. Houston, there's it is doubling because energy conservation. If you increase input power, there's an increase at the electrical terminal. Okay, and then that power cause some change. Of course, there would be some other solutions, but in this solution, I got the idea. In this solution, I want to use the second approach. I want to use this formula because this guy doubled. This is constant, this is constant, this is constant. That is amplitude of this guy kept constant since there is no change in field current. So if this guy doubles, there is some change in this, and it is easy to calculate new delta. Okay, let's do it. Let me find the equation here. That is the power equation, and I wanna calculate delta 2, which is new value, and it can easily be taken out here. So it is 7.1216 degrees. Again, it is positive due to generator operation. Degrees positive due to generator operation. The second question is answered. Now, what's the new value? New value is 7.167 degrees. The old value was 3.576 degrees. So when you increase input torque, doubled input torque, there is an increase in delta, as you see. There is an increase in delta. If you keep input torque increasing, there will be increasing delta. As you know, the limit is 90 degrees. When load angle reaches 90 degrees, the synchronization between those two magnetic fields, between stator and rotor magnetic fields, connection will be lost, synchronization will be lost. After that, generator can deliver no power to the system. That is a kind of fault. The generator must be tripped off from the grid. Now we have calculated this guy, and as a third question, and it was the most difficult one, 30 points. In this new case, I mean that is the new case, second case. In this new case, write the angle phi 2, which is the angle of the current, yes, with respect to voltage. Yeah, we know phi is the angle with respect to current's position with respect to reference, which is voltage, in degrees. And please take care its sign, whether it is lagging or leading. It is important. Take care the sign. Okay. It looks a bit difficult possibly, but there is only one choice to calculate current. Houston, I said current, but a question asks phase angle. Houston, that is a trick. That is a trick. How can you reach new value? Let me say phi 2. How can you reach that? If you know reactive power, active power, you can get. But you don't know. You don't know any information about reactive power, but you know some information about the active power. Initial value of phase angle was 0. It was operated as pure ohmic, but after increasing torque, machine go under a different operating condition, and possibly there is a reactive power exchange between network and generator. In the second case, there's a reactive power exchange, but in the first case there were no reactive power. Okay, so you don't know any information about reactive power, so you cannot use this equation. What is the phase angle? Phase angle is the angle of position of the current with respect to reference, which is voltage. So it is the angle of current. Houston, that is I need this guy. Okay, if you calculate that guy, you can easily calculate the argument of I1 phasor is equal to new or second value of the phase angle. So our new objective is to calculate new current. New current again comes from the equation here. That is the generator relation. Armature resistance is neglected in the question, so all those are phasors, do not forget. I don't know what the phase angle is. I leave it implicit. So, but I can calculate delta nu. We have already calculated. I'm sorry. We have already calculated. Here it was in the second case. So I already know, that is the new case. I already know the magnitude. Magnitude is equal during all operations. Magnitude is equal. And then Houston, everything looks clear. Let's go and calculate the current. But we should construct the equation. Let me write it down here. EMF is equal to, let me just make a logical equation here. Terminal voltage plus J, or we have used I here, I times current times excess. That was the generic equation, okay, but we know EMF, yes, here it is, and we should make this, convert this into a phasor. Ladies and gentlemen, mass multiplied e times e to the j or I complex e to the what's happening here? Let me copy this guy. Here's something, a syntax error. Yes, remember, let me remember you. EF phasor can be written as EF magnitude times cosine delta nu plus j sine delta nu, or EF e to the j delta nu. Angles are in radians, do not forget radians. That is the Euler formula, you remember, that is Euler formula, that is Cartesian expansion. So let's complete the equation. We have made it phasor. There is no need to make any change, it is constant. My aim is calculating I1, that is complex parameter, and XS is known. So new value, let me say I2, let me say I2, new value of the current is will be calculated here. That is the new value. If you solve current here, that is the current having such a value, amperes. And Houston, you can see that current has an amplitude, magnitude of those two guys, here it is, and current has an argument, an angle, which is new phase angle. It is 2.692 degrees. Houston, it is positive. Positive phase displacement means capacitive operation. Generator has some capacitive loads in the network operation. Generator supplies some capacitive elements. I mean, in the second case, phase angle is positive. That means there's a leading current. That means here are some capacitive loads, and generator also delivers some negative reactive power to them together with some active power. Okay, and here we have just calculated the new phase displacement. It was hidden, it was a bit difficult, as you see, and we have interpreted the sign of the angles. There would be some other solution approaches, but I have discussed them in detail. There is also a Turkish version of this video you can watch. Perhaps it has got more detail, I don't know, so you can follow also this one. Okay, that's the end of the first part.